Greetings. In this video I want to talk about the moment of a force about the point in 2D space in this case. Because in 3D space we will actually need to use something more than just multiplication, as we know. There will have to be used something called cross product, which involves for example a determinant, and it works for 3D vectors and moments for points in 3D space, all of that. But now let's just consider 2D space, and let's consider some concrete example here. So we're not talking about some necessarily like a rigid, let's talk about the rigid body because the force has to be translated towards the point and so on. But we won't take into account some equilibrium because more things would have to be calculated when I talk about force. There has to be an equilibrium in the y direction, x direction, which is a topic for another video. We will actually take care of that later at another point. But in this one, let's just focus on a point and a force, and let's just see how the moment can be calculated from that. So if there's a point A and there's some rigid body connecting it to a force, for example, like this, and the force has 5 newtons, and it's given by an arrow, so it means it has exactly this direction, and the size is given here. I could call it F equals 5m, so the force would be called F and magnitude 5 newtons, but I just chose, you can call it anything, F or whatever letter or whatever name, but in this case, just to simplify it, I'm just talking about its magnitude because there's no other force, so no reason to call it, but at least the point, I called here the location. So the general definition for a moment is the perpendicular distance from a force's action line to the point times the magnitude of the force. So what is the action line? Action line of a force is, we have this direction of the force, there's some magnitude of it, that's kind of geometry given by the length. If we prolong the length twice, it suddenly would have 10 newtons in this case. And the action line is the direction of the force, which the arrow gives. It points in this direction. So we prolong it like this. Although the magnitude is not this big, it's just till here, we can still prolong the line kind of, to prolong the direction, the action line. So the force could be like moved along this line theoretically. And what I want to do here is show how to calculate the moment that this force creates for this point. So in general, moments are called m. Let's just make it simple like this in this case. And it's defined as F times some perpendicular distance d. So in this case, it turns out that actually the perpendicular distance is given straight here, as long as I know the length of this line. So this is the d. The perpendicular distance is, we have a force, and we take some perpendicular line that directly will go to the point that around which we want to take care of the moment. So because we have this body that connects it directly to the point, and the force is completely perpendicular, exactly this should be perpendicular to this line here. Therefore, this distance is exactly what we need. Now, if the force was slightly like this, a different angle, then things would have to be different, because if the force, for example, was like this, then we would actually need the action line, because a perpendicular distance would not hit the point A. We'd have to prolong it a bit and now find the perpendicular distance, which would be this. But the calculation would be harder because we would have to get to know this magnitude of this line. So we would have to perhaps use some trig functions and so on. But we're not doing that in this case, although that could also be possible. So just to finish up this calculation, what we have to do is realize that there is a perpendicular distance from a force to a point and multiply it by the force's magnitude, which is the 5 newtons. So if this distance, I say it's 1 meter, then simply I will plug it here. So the moment for point A caused by this force of 5 newtons that is perpendicular to the line connecting to A already, which is a lot of things have been taken care of, then it's 5 newtons multiplied by 1 meter, so it's 5 newton meters, where the moment unit is this, newton meters. Under the units of newtons and meters, it's newton meters. It's force times distance. So that's the moment on A, at A, caused by this force. Now, another example could be taken into account because we could have some point A, and it could be connected, and there could be, as I showed, the force F like this, and it will have again 5 newtons or whatever it is called, F, or I just say some force with this direction and this magnitude. Direction given by the arrow, so that's visual completely, and 5 newtons given here. So we know this is D, so this would be D. Even if it was 1 meter, for example, let's say it is 1 meter to give concrete values, we need the shortest distance from the force's action line. When the force would be long enough, then we would not need to take into account the prolonging, the action line, in other words. Because there could be some, it would reach all the way here and it would go straight here perpendicularly. But because the force just reaches here, we need to kind of create this action line that belongs the direction, or at least shows the direction of the force, but as far as we need. And now get the perpendicular distance, because that is by definition the shortest distance from the force's action line to the point. So we need some line like this that will be perpendicular to the action line of the force, because this is our force. So now the moment is going to be something like, basically we're taking just this segment's length. So we're just taking care of this segment, and let's call it for example E. So this segment, this length, would actually be what we would now use for the moment. So if this was 5 newtons, now the moment for point A caused by this force will be 5 newtons times E. And there's again more ways to actually approach this. Another way to approach it is, and this is probably better to take care of in another video, is that we will break out this force into y and x components, because the distance is going to be in the x components, and then we will take the moment kind of in that sense, because the x component will go straight through the point, and when a force goes straight through a point, it has no moment on the point. Only a force that has direction such that it doesn't go through the point has an effect. But if we are able to bring out this force into a part that goes straight, that gets cancelled out, and the other part that 100% gets absorbed because it's already perpendicular, then we will only take into account this part. So either now, in case that the force has a different direction, we create this action line and we take the perpendicular distance from the action line, the shortest distance from the action line, perpendicular distance from the action line to the point, and use that for the calculation of the moment. Or what we can also do is, and will also be equal to, let me now call this F. And I'll just state here once again that it's 5 newtons, just for the F to take up less space. We can break it up into something called F sub y, which would be its y component, its only vertical part, because the force can be represented equivalently, such that we have a y part of it and an x part of it, and an x part of it, fx, where this fx will be the projection of this vector down on this x-axis, for example. So we see that the horizontal direction gets taken care of like this, and the vertical like this. The vertical like this and the horizontal like this. It creates a rectangle in this shape, actually, in this case. So what we now have is its vertical component and its horizontal component. And as I said, the f of x, well, what is the perpendicular distance? Perpendicular distance from its action line to A. If I prolong that action line, it goes straight through A. So the perpendicular distance is nothing, it's just 0 here. It actually is the line that goes straight through A, so that there is no effect from f of x. But all of the effect will be from f of y directly. So instead of saying that, and there's some angle here, let's say theta, and so all the effect will be taken care of by Fy. So out of this, and it has 5 newtons, some part, the vertical part of it, will have all the moment effect. Now, what will it be? Again, I can say 5 newtons, but Fy is going to be 5 newtons. And how do we get the vertical component? Is defined as times sine of the angle that the force makes with the horizontal axis. So in this case, this angle, theta. So times sine of theta. 5 newtons times sine of theta, or to make it like just a number here, this will actually evaluate into a number. So this together will be a number times newtons. That will be the y component of f. So in this case, again, I can just use d, which is 1 meter. So it'll be 5 times sine of theta, which will be a little less than 5 newtons, times not e, but we can just use d, times 1 meter. So what will it end up being is going to be, already we know it's going to be 5 Newton meters. 5 Newton meters. But we will have to scale it down by sine of theta. This will affect the number part, the 5 here. It will, sine theta will be less than 1, and it will decrease the value of the f. The value of fy will be less than f.